Hi, this is Dr. Jivikas Paul. In this session, we are going to study about the effect of shortening of rib in two-hinged parabolic arch. The arch is made up of elastic material. Shortening of rib takes place. An arch is also like rib in our skeleton. Due to shortening of rib, the horizontal thrust developed will be shortened. So we have to find the horizontal thrust that is developed due to shortening of rib. Rib shortening is due to mainly normal thrust developed in the arch. So due to the normal thrust developed in the arch, there will be shortening of the rib. So due to the shortening of rib, the horizontal thrust will be shortened. We need to find this shortened horizontal thrust, H value. So we know that strain energy formula is the integration mx square ds by 2ei. Here we also need to consider the normal thrust. Therefore, strain energy equal to integration nx square ds by 2ae, where nx is the normal thrust. We know that normal thrust equal to h cos theta plus v sin theta, and mx equal to beam moment minus h into y. Mx equal to beam moment m dash minus h into y. So total strain energy U equal to integration mx square ds by 2ei plus integration nx square ds by 2ae. If the support is unyielding, then the horizontal displacement of the arch is 0. Therefore, dou U by dou h equal to 0. Dou by dou h integration mx square ds by 2a plus dou by dou h integration nx square ds by 2a equal to 0. Therefore, we can take dou by dou h inside. Then we will get integration 2 mx dou mx by dou h ds by 2ei plus integration 2 nx dou nx by dou h ds by 2a equal to 0. But we know that mx equal to m dash minus hy. If we differentiate with respect to h, we will get minus y. If we differentiate normal thrust, we will get cos theta. Dou nx by dou h equal to cos theta. So substituting in the above equation, we'll get integration m dash minus hy into minus y ds by ei plus integration h cos theta plus v sin theta into cos theta ds by ei equal to 0. Therefore, minus m dash y ds by ei plus h into integration y square ds by ei plus integration v sin theta cos theta ds by ei plus h integration cos square theta ds by ei equal to 0. Therefore, we will get h equal to integration m dash y ds by ea minus integration v sin theta cos theta ds by ea divided by integration y square ds by ea plus integration cos square ds by ea. Neglecting the effect of shear, we will get h equal to integration m dash y into ds by ea divided by integration y square ds by ea plus integration cos square theta ds by ea. At the crown, we know that theta equal to 0 and area of cross section is very small at the crown. Therefore, assuming a by cos theta as a constant, say am, that means am equal to a by cos theta, we can write integration cos square theta ds by a equal to integration cos theta ds by e am, because am equal to a by cos theta, which is equal to integration 0 to l dx by e am, where dx equal to ds cos theta. Therefore, applying limits, we get l by e am. Therefore, h equal to integration m dash y ds by a divided by integration y square ds by a plus l by e am. If both yielding of support and rib shortening are considered, we can write h equal to integration m dash y into ds by ei minus delta divided by integration y square ds by ei plus l by eam. Therefore, h equal to integration m dash y ds by ei minus kh, because delta equal to kh divided by integration y square ds by ei plus l by eam. Therefore, we'll get h equal to integration m dash y ds by ei divided by integration y square ds by ei plus l by eam plus k. K is for yielding of support here and L by EAM is for rib shortening. If there is effect of temperature, we can add L alpha T also. Now we'll see a problem on this. A 2-hinged parabolic arch of span 50 meter and rise 5 meter is subjected to a central concentrated load of 60 kilonewton. It has an elastic support which yields by 0.0001 mm by kilonewton. Take E equal to 200 kilonewton per mm square, I equal to 5 into 10 power 9 mm power 4, alpha equal to 12 into 10 power minus 6 per degree Celsius, average area AM equal to 10 power 4 mm square, and assuming secant variation, calculate the horizontal thrust developed when the temperature rises by 20 degrees Celsius. First case considering rib shortening, second case neglecting rib shortening. So in this problem there is temperature yielding and also rib shortening. Therefore the formula is h equal to integration m square y ds by a plus l alpha t by integration y square dx by a plus l by eam plus k. K for yielding of support, L by eam rib shortening, L alpha t for temperature. So first of all, solving for integration m dash y dx by ei, which is equal to 2 times integration 0 to 25 m dash y dx by ei, because we will take two sections, left side and right side. Therefore m dash equal to 2 times 0 to 25 30x 4h by L square into lx minus x square dx by a. So solving this, we will get integration m dash y dx by ei as 0.078. Similarly, solving integration y square dx by ei, we will get 2 times 0 to 25 y square dx. Therefore we will get 666 divided by ei. Substituting e and I values, we will get 6.66 into 10 power minus 4. Here we need to convert e and I in terms of meters. First case, considering rib shortening, h equal to integration m dash y dx by ei plus L alpha t divided by integration y square dx by ei plus k plus L by eam. Substituting all the values, we will get h equal to 113.842 kilonewton. Similarly, neglecting rib shortening, we need to neglect the L by eam term here. So we will get 117.5 kilonewton.